The first thing you need to know is about the unit of charge. The SI unit of charge is called the Coulomb. We use a capital C to abbreviate that, and 1 Coulomb is equal to the charge of 6.35 times 10 to the 18th electrons. Now I hope you realize right now that that's a really big number. That's a lot of electrons, right? And I know an electron is a very small thing, but we know that the electron is the whole thing with electricity. It's the big deal. That's where the charge is carried. And so 1 Coulomb is equal to 6.35 times 10 to the 18th electrons. It is the charge of that many electrons. So that's a really big charge, and to give you an idea of just how big that charge, well, I'll give you an idea of how big that charge is in just a minute, but it's a massive, massive charge. Most of the things that we deal with, in fact, all of the things that we're going to deal with in this class that relate to charge are not on the order of coulombs. Everything is going to be less than 1 Coulomb because this is such a big charge. And so you need to know another number that we call the elementary charge. The elementary charge, you need to know that term. That term means the charge of 1 electron or 1 proton. It's equal to as far as the charge amount, it is 1.6 times 10 to the negative 19th coulombs, and that is the amount of the elementary charge. That is a number that is in your formula chart, and you're going to need to know it. So, for instance, if a problem says if it involves 1 electron or 1 proton, a lot of times they won't tell you this, and you'll just need to know that this is the charge of that proton. So 1.6 times 10 to the negative 19th coulombs is the charge of 1 electron or 1 proton. The only difference with a proton is you put a positive in the front. Obviously with an electron you put a negative in the front, but the amount of charge is the same thing. And then 1 Coulomb, the unit of charge, amounts to a whole bunch of elementary charges, 6.35 times 10 to the 18th elementary charges or electrons. Again, 1 Coulomb is a massive, massive charge. A lightning bolt, if I was to ask you how much charge do you think is contained in a lightning bolt, something that can harm you, it can kill you very easily, that's only about 10 coulombs. And I shouldn't throw in the word only, because 10 coulombs is a massive amount of charge. Everything we're going to be dealing with is much less than that. So 10 coulombs is a huge amount of charge. So we're going to be dealing with things on the order of less than a coulomb. We're going to have to be doing conversions with this. The purpose of this section of talking about Coulombs law is, as we've talked about already, electrically charged objects can exert forces on other charges over a distance. And these are interesting forces. We've talked about the difference between contact forces and long-range forces before. And we've talked about gravity. Gravity is a long-range force. It does not require matter. It does not require you to be in contact with another object for gravity to be in existence. However, gravity is only an attractive force. This electrostatic force can be both attractive and repulsive. And it's over a distance. It's an interesting phenomenon that 2 charged objects can exert forces on each other over a distance, and it's something that's kind of hard to understand. Just like gravity, the force gets stronger as the objects get closer together. Okay, so the closer, if this is a positive and this is a negative, the closer we bring them towards each other, the stronger the force gets. It's kind of like magnetism. We can think about it in terms of magnetism, but it isn't the same thing. I don't want you to get those confused. The closer they are together, the stronger the force is. And by the way, that was also true with gravity. The gravitational force diminishes as the 2 objects get farther apart. And we've already said this. You know that the like charges cause repulsion forces, repelling forces, and opposite charges will attract each other. So if this is a positive, this is a negative, they will attract. Positives, and negatives will repel each other. Coulomb's law in words says this: the force on 2 charged particles depends on, number 1, the amount of their charge, and number 2, the distance between them. And you'll find this equation to be very, very familiar. It looks like this. This is equation number 26 in your formula chart. And you might even want to put in your notes a subscript E under here to differentiate it from the gravitation equation, because this formula looks very, very similar to the gravitation equation. K times Q1 times Q2 divided by D squared. Here are your variables. F is the electrostatic force between the charges. Since it is a force, it is measured in newtons. K is the electrostatic constant. We've talked about that already in the first set of notes. This constant is in your chart. It's number 74 in your chart. 9 times 10 to the 9th, and you don't really have to worry about these units. The units are just what they are to make this equation work out. 9 times 10 to the 9th. Once again, that's a very big number. It's the electrostatic constant. So we're going to get pretty big forces here. It's a strong force. The Q's are charges, charge 1 and charge 2. Obviously, Coulombs law has to be between two charged particles, and actually if we go into AP, you can have forces on 2 or 3 or more charged particles, and that gets very, very complicated. In this class, we're only going to do 2 particles. But these numbers have to be in coulombs, and I want you to write yourself a note right here that, remember, I said that the charge of a coulomb is extremely large. We will almost never have anything in coulomb units. Most of the things we'll be given are on the order of millicoulombs or microcoulombs, and so we're going to have to convert to coulombs in order to put those numbers into this equation to do anything with it. And then D, as you can see, is the distance between the two objects, and we are going to square that distance. So again, look here at your chart. I want you to see, here's number 26. This is the electrostatic force equation we just learned. And compare that to number 16, the gravitation equation, which we dealt with a while ago. They're almost exactly the same equation in terms of algebra. See if we can get this on the same screen. G times the product of the masses divided by the distance between them squared. K times the product of the charge divided by the distance between them squared. So there's only really two differences. The fact that the force, the electrostatic force, is dependent on charge, whereas the gravitational force is dependent on mass. And then, of course, the two constants differ, G and K. And we talked about earlier that K is 10 to the 20th times larger. So we're going to get potentially pretty large forces with the electrostatic force. But the algebra is exactly the same. So we're going to have numbers that work together here the way that we did this in terms of algebra and putting it into our calculator. If you had problems with that, you might have the same problems with this equation, and we need to get those worked out. So this is the electrostatic force equation. Also write a note to yourself with this equation. There are no negatives to be put into this equation. And I know that doesn't necessarily make sense to you because you say, well, there can be negative charges and positive charges, right? Well, yes, that's true. However, let's consider something real quick. Look now here at, let's just imagine that I have two charged particles here. Force is a vector quantity, right? Which means force has a magnitude and direction. Forces have magnitudes and directions. We understand that. Every time we've reported forces before, we've said, 10 newtons north or 3 newtons to the right. We've given a direction with it. Well, we need to think about this electrostatic force. Okay, let's imagine that, let's just say these both are positive charges. What's the direction of the force? Can we give one direction of the force? Well, you can, but it's not the same as the directions we've given before. We can't say left, right, up, or down. Because if I say the force is to the right, that means that both of these will be drawn to the right, and that's not what's going to happen. I think we can all readily see that these two objects are going to be repelled away from each other, and therefore repel is the direction. There's only two possible directions with the electrostatic force. The objects are either going to repel or they're going to attract. And it was the same way with the gravitational force. When I had you sitting here above the Earth, the gravitational force really doesn't have a direction, because it's not that you're being pulled down toward the Earth, it's that you and the Earth are pulling yourselves towards each other. And so it's simply an attractive force. Therefore, we really don't care about the direction because we know the direction. So with the gravitational force, there's no left, right, up, or down. It's simply repulsion or it's attraction. And you don't need negatives and positives to give you that. You should be able to tell from the problem you're given if you have two positives or two negatives, that those are going to be repulsion forces. They're going to repel each other. However, you should know, if you're given a positive and a negative, that that is an attractive force. These two are going to attract each other. Once again, it's not that one is pulling the other one towards it. This doesn't happen. It's that they're both pulling each other towards each other, almost as if there was a slinky in here. Remember our discussion of a slinky when we talked about the gravitational force. These two objects will meet in the middle, and where they meet depends on the relative magnitudes of their masses as well as their charges. But the direction here would be that they are going to attract each other. Not to the left, not to the right. One is going to the left and one is going to the right, but it is simply an attractive force. So we don't put any negatives into this equation because we understand what the direction is. It's either going to be attraction or repulsion, and you should be able to make that decision based on the problem that you're given. So let's move on from here to that check for understanding part in your notes. You need to understand the proportionality relationships between this equation. In other words, the question is, how does changing the charges of the object affect the amount of force? And how does changing the distance between them affect the amount of force? Hopefully you remember that there's to be an understood 1 under here. Anytime today? There we go. There's an understood 1 under here. And so anything that is both on the top, or if they are both on the bottom, those two variables are directly related to each other. Whereas if you have two variables that are juxtaposed top and bottom, where one is on the top and the other is on the bottom, like F and D, those are inversely related to each other. So F and D are inversely related. That means if distance decreases, that means the force is going to increase. This is the same concept as with the gravitation equation. We understand this practically. With gravitation, the closer the objects are together, the stronger the force gets, and it's the same with the electrostatic force. The closer they are together, the stronger the force gets. So let's look at this check for understanding. Your choices here are basically stronger or weaker. The closer the charges are, is the force stronger or weaker? And then if we're going to change the charges themselves, does that make the force stronger or weaker? And then answer this question also. Pause the video for about 30 seconds and see if you can answer these. All right, so let's talk about these. The closer the charges are, well, we're messing with the D there, right? So if we get them closer together, that means the distance is decreasing. Distance is inversely proportional to the force, so that means the force should increase. That means that it's going to get stronger. The closer they are, the stronger the force. What about the charges? The larger the charges, the blank the force. Well, we look back, charge is on the top, force is also on the top. So these are directly proportional. Whatever happens to one, the same happens to the other. So the larger the charges are, that means we're increasing the charge. The force should also increase as well. So stronger is what you should have there. Is force a scalar or vector? The answer is, it is definitely a vector. Force is always a vector. It's just that, remember, like I said, it's not going to be left, right, up, and down. There are only two directions. There are only two directions with electrical force, and those are either attraction or repulsion. Attract or repel. The force between two particles is equal in magnitude, but opposite in direction. Just like the gravitational force. Remember with the slinky example I did with the gravitational force, the force is the same in both directions when we're pulling those two objects towards each other or pushing them away. Their relative acceleration depends on their mass, according to the F equals ma equation. So the last thing I want to cover on this video is this part of the notes, and in your notes it says important. And we have here important information you'll use over and over and over and over and over. I'll give you the masses, but you need to know blah, 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 blah. Well, here's the deal. It's not really as important as this says. If we were an AP, yeah, but basically, you're not going to need any of the masses, so cross those out. We're not going to use those. They do come, it's not that they're not important in nature. They do come into play, but in this class, we're not going to use them. So we have protons, electrons, and neutrons. You're given their masses. We're not going to need those. And then this table also, you're given the charges of each, and you don't really need that either because that's in the equation chart. 1.6 times 10 to the negative 19th coulombs is the elementary charge which you have up at the top of your notes, and if it's an electron, you just throw a negative in front of it. And if you forget that number, once again, it is in your chart. And a neutron, you should know, is neutral, therefore the charge is 0. So really, To be honest with you, this entire chart you can probably just get rid of because you have this information already.